In this video, we will discuss about dimensionality reduction. We'll first discuss about various methods which are available for dimensionality reduction, and later we will particularly focus on PCA based dimensionality reduction. We'll see PCA, which is principal component analysis, using both covariance method and also using singular value decomposition. Finally, we will see the implementation of PCA using SVD, which is the computationally efficient way of doing the PCA. Dimensionality reduction is the process of reducing number of input variables or features, which means to remove the unnecessary, redundant or noisy features which are irrelevant in a dataset by preserving as much relevant information or structure as possible. So let us see how it can be done and what are the methods which are involved. So broadly, it can be categorized into two categories. One is feature selection based and feature extraction based. In feature selection based, these methods do not change the feature values. They exactly retain as it is, except that they select relevant features. Whatever are the existing ones, they select from the set rather than modifying the features. Whereas feature extraction based depends or modify the features so that it transforms into a more relevant features and thereby avoid the unnecessary redundant information. There are three different categories in feature extraction. One is linear methods, the other category is non-linear methods, and the third category is neural network based methods. In linear methods, we have principal component analysis, PCA, singular value decomposition, SVD, linear discriminative analysis, independent component analysis, factor analysis, etc. In non-linear methods, we have kernel PCA, TSNE, and so on. In neural network based, we have famous autoencoders, variational autoencoders, and deep autoencoders. In this video, we will be particularly focusing on PCA based dimensionality reduction. We will also see how SVD is very much close to PCA and how PCA can be implemented using SVD. Let us now discuss about principal component analysis. As we have discussed earlier, it is a linear dimensionality reduction technique where it transforms dataset into a new coordinate system where the axis of this coordinate system comes from the greatest variance. So the first greatest variance gives the first major axis and the second greatest variance gives the second axis. So we would like to transform each of these dataset into that particular coordinate system. We can view PCA as that, and the second definition we can see as to transform a set of correlated variables into a completely uncorrelated variables called as principal components. So many, as we have seen earlier, a lot of features are correlated, can be correlated, and we would like to reduce those redundancy by moving from correlated variables to the uncorrelated variables. So these are two different views. Let us see more mathematically and understand how PCA is computed. Let us see how principal component analysis can be computed. Let's start with this data set. We have a number of points here. Our job is to find out these axes along which there is maximum variance and also second maximum variance. So since it's a 2D image, we are showing it as an ellipse, but if you go into higher dimensions, we'll have other axes also. So let's see how we can compute these axes along which there is maximum variance. Let's consider a dataset X represented in the form of a matrix of dimension n cross d, where n represents number of samples and d represents number of features. Our first step is to mean center the data. We compute the mean along all the samples and subtract that from each of those so that it becomes mean centered. And we compute the covariance matrix also. So let's see how we can compute these axes. First, let's formulate this as an optimization problem. So if you see this, our job is to find out this W vector along which we are trying to project, and our goal is to actually maximize this variance. Once after projecting each of these data points onto this axis, we would like to see along which is that axis which gives the maximum variance subject to the condition that weight vector is equal to 1. And this we do it because since we are maximizing it, it can go until infinite. So to have a constraint, we are using this. But our job is to how do we maximize the variance of the and what should be the axis w, such that the projection of each of these data points onto this axis will result uh, into a maximum variance. So that is the axis which we are interested in, and this problem can be formulated something like this. We are just representing xc transpose xc as c here, and this can be solved using Lagrange multipliers as follows. So this constraint has been brought into the main objective function, and when you apply gradient and when you solve it, we get an equation something as follows: cw is equal to lambda w. This is what eigenvalue definition or eigenvectors definition, ax is equal to lambda x. So we are essentially trying to find out the eigenvectors of this matrix C, and those are the vectors which are going to give us the maximum variance for this projected data. So towards that, we find out the eigenvectors of this matrix C, and thereby obtain the all these axes along which there is maximum variance. The matrix C here is a symmetric matrix, and we can choose orthogonal eigenvectors to this matrix C, and so the w vector would be an orthogonal eigenvectors, and those form these axes of this ellipse or in higher dimensions. So let us now understand some geometric meaning of what is happening here. So we have a set of data points, those have been spread along certain directions, and mathematically we came to understand that if you are able to find out the eigenvector of a maximum eigenvalue, that vector is going to give the spread of the data along a particular direction. And why is it happening? It is because when you project each of these data point onto this vector w, that's what we are doing here. When we multiply xc with w, each sample, each row in xc is a sample, and when we are multiplying that particular row with w, we are multiplying each sample with this w vector. So which means to do a dot product between each sample and w vector, and this dot product would be maximum when the angle subtended between them is less. So when the data is along the w vector, we will have this maximum value. So we are therefore our eigenvector here is giving you that direction along which when you project the data, you will get the maximum variance. So in the same way, for the second eigenvector will give the second maximum variance, and so on. Let us summarize what we have discussed in principal component analysis. We considered an input data in the form of a matrix of dimension n cross d, where n is the number of samples and d is the number of features. We centered the data, and we later computed the covariance matrix, and we have performed eigenvalue decomposition to the covariance matrix, where q indicates eigenvector matrix, where lambda indicates the diagonal matrix with eigenvalues as the diagonal elements. And out of these eigenvalues, we have chosen the k maximum eigenvalues and its corresponding eigenvectors and constructed the matrix qk. And we eliminated all of the other components. This is how we do dimensionality reduction, where we remove the unnecessary redundant directions, and we focus only on the more relevant components. So this is how we project, where we multiply with the qk matrix, and as qk matrix is orthogonal matrix, so when you multiply with its qk transpose on both the sides, you can get back this centered matrix, and if you add mu, you can get back the original matrix X. So in this way, this was the summary of what we have done in principal component analysis. Let us now discuss two different ways of computing PCA. One is the covariance based computation of PCA, and the second is SVD based PCA. In both the methods, we'll start with our input matrix X, we center them, and later we compute covariance matrix in the case of covariance based PCA, and whereas in SVD we don't do that. In the later step, we compute the eigenvalue decomposition for the covariance matrix C, and whereas in SVD based method we do singular value decomposition for the matrix XC. If you observe, Q matrix is nothing but the eigenvectors of the covariance matrix C, which is XC transpose XC. In the same way, in V is also, we know that V is constructed by computing the eigenvectors of XC transpose XC. So in a way, both are doing the similar things, where we are utilizing the eigenvectors of the matrix XC transpose XC. So we get principal directions in the matrix Q and V, and variance values, or the how much is the variance in the data, is quantified using eigenvalues in the case of PCA based method, whereas in singular value based PCA, our singular values quantify the amount of variance. In fact, lambda and singular values are very much related. You can compute singular values by taking the square root of the lambda values. So out of the many principal components, we take the k dominant PCs by choosing the eigenvectors of the k maximum eigenvalues. So those eigenvectors are placed in Qk and Vk in the case of SVD based PCA, and projections are calculated as follows, where z is equal to xcqk, whereas here z is equal to xcvk. So later we can do the reconstruction, as Qk is orthogonal matrix, and we can re-add the mu term to get back the non-centered data. So PCA is almost always implemented via SVD because there is a computational advantage as compared to covariance based method. And also PCA eigenvectors are nothing but the SVD right singular vectors. Just now we have seen the right singular vectors and the PCA eigenvectors are similar, and PCA eigenvalues is equal to the squared singular values. So this is how PCA based covariance based method and SVD based PCA are related. Let us summarize the steps of dimensionality reduction using SVD based PCA, and we'll solve one problem. So as you can see here, X is our matrix, and when you center we get XC. We apply SVD to compute U sigma V transpose. We take the top k singular values and its corresponding singular vectors, which we obtain from Vk, and we project that data and we obtain the matrix Z. This is how we get the dimensionality reduced data set. So let us see one example to solve it. Consider the matrix X with 3 samples and 2 features, and as you can see they are very highly correlated, and when you do mean centering, this is what we get it, and when you apply singular value decomposition you get U sigma V transpose. But as you can see there are only one singular value, the other singular value is 0, so we can eliminate this redundant data, and we can only consider the singular vector of the maximum singular value, which is from the V. And when you do that, we have something as follows. So we consider only one singular vector V1 and constructed the Z matrix, and when you try to reconstruct, we get X approx similar to our centered data, and when you add the mean you get back to the original matrix X. Let us now discuss how PCA is implemented using SVD in Python. We are utilizing the libraries NumPy and matplotlib. So first we created an sample NP array with 5 samples and 2 features as a 5x2 matrix, and we printed it here. We computed the mean centering along axis 0 across all samples. We got the matrix XC. And then we apply the singular value decomposition for the matrix XC. So as we have just now seen that we can use SVD also to compute the PCA. We are invoking this method SVD, which is part of linalg, and this library is part of NumPy library. So we compute U sigma V transpose for this matrix XC, and once we obtain these singular values, we utilize the V matrix which contains the principal directions, and later we take only since we have 2 columns there is scope for 2 principal components, but we have eliminated the redundant one, and we have only chosen the one which has the maximum covariance value, maximum singular value. As you can see here, the two singular values 2.635 and 0.46. So we are eliminating the eigenvector, eliminating the vector corresponding to this singular value, and we are utilizing only the vector corresponding to 2.63. So when you, that's what is being done here. We are taking only the first singular vector of the first maximum singular value, and later projecting this data to construct the matrix Z, and later we use it once again to reconstruct back the data. So by just using the one principal component, we are able to reconstruct the original data. Let us see what sort of error it has as compared to the ground truth. So 2.36 and 2.54. So our original data was 2.5 and 2.4. So it is almost close. So in this way, wherever we have redundant data, we can eliminate by appropriately choosing the dominant principal component and reconstructing the matrix. So this is how PCA is implemented in Python. Let us see one of the application of PCA called Eigenfaces. Eigenfaces can be used for face recognition. So let us see how it works. So eigenfaces are a set of basis faces that capture the most important variation among a collection of face images. It is actually a low dimensional representation of the face images which capture the essential information and eliminates unnecessary information. So let us get the intuition by taking a small example. So let's consider 1000 face images which are grayscale and of size 100 cross 100, and all these images, we make sure that eyes and nose are aligned, and each image can then be represented as a 10,000 cross 1 vector which is high, and there is a lot of redundant information. So we can use PCA to represent in a low dimension, and this low dimensional representation of each face is called as eigenfaces. So we use this representation to do face recognition. So let us see it. So let's consider, we know already the steps involved in computation of PCA, which is to compute the mean, center around the mean, and compute the covariance matrix, and compute the eigenvectors which corresponds to the eigenfaces. So here, so all these images which are listed here are the eigenfaces. So this is the mean face and this is the eigenface. So when I say eigenface, this is the low dimensional representation of the original face, and in practice we compute these by computing the V matrix in SVD, and once we obtain the low dimensional representation of eigenfaces, we can represent any face in terms of this eigenface, and we can obtain the weight vector corresponding to every face, and these weight vectors can be later used for face recognition. So suppose if you represent a image in terms of eigenfaces, and if you reconstruct, it would look something like this. Depending upon how many eigenfaces you have used, it shows the amount of clarity in the images. So let us see how this works for face recognition. So in face recognition, when you get a new test face, we try to compute the weight vector by representing in eigenfaces, and we compare this weight vector with the already stored weight vectors, and thereby recognize the test face with the existing set of images. So this is how eigenfaces work for face recognition. That's how eigenfaces can be implemented. Here we are using various libraries to implement this. So we are using OpenCV, NumPy, Matplotlib. So we have all the face images here in the faces directory. We are reading each of those faces using the OS library and using OpenCV, and we are computing the mean and centering each image to its mean, and we are applying SVD to compute the PCA. As we know, PCA can be efficiently implemented using SVD. So we are invoking the SVD function as part of linalg library, which is part of NumPy, and computing U, sigma, and V transpose. So an important thing to note is our eigenfaces are nothing but this V transpose. So each row is an eigenface here. So we are trying to display here 6 eigenfaces through this matplotlib, through this function, through this loop. And later we are setting k is equal to 20, which means we are trying to reconstruct using 20 eigenfaces and reconstruct all the eigenfaces multiplied by weight to obtain the reconstructed image. So later we can also use these weights for recognizing any image, where you send a test phase, compute the weight vectors, and compare it with all the weight vectors of the images which are there in the database, and recognize the appropriate image. The output, I'll run it once again. So this is the mean phase. So these are the eigenfaces. So 6 eigenfaces has been displayed here, but we have computed 20 eigenfaces. So this is the reconstructed using 20 eigenfaces. So let us change this eigenfaces number and see how the reconstruction error changes. Suppose let's take 100 eigenfaces and run this. So if you run this is the mean phase, and eigenfaces, I am displaying only 6 eigenfaces here, although we computed 100, and this is the reconstructed eigenface. As you can see, the face is much more proper. So we have increased the number of eigenfaces and its corresponding weights. So the summary is, we can use these eigenfaces to represent any face image, and also we can use this weight vector for face recognition. So if you have any test image, you compute the weight vector by representing in eigenfaces, and compare this weight vector with all the already stored image weight vectors, thereby recognize the faces. So this is how PCA can be used for face recognition in eigenfaces, using eigenfaces.